No,
That was right.
like the comma's in the wrong spot. So the amount of energy to boil it is considerably more than the amount of energy it takes to melt it. Which makes some sense. If you're turning it into a gas, you are getting the particles even farther apart. And then 100 degrees Celsius up to our final temperature of 120 degrees Celsius. And let's see, steam. Delta T, so 0.5 times 1996 times 20, which is 19,960 joules. And so our grand total is, or is there a mistake there? Say it again.
1,534,210 joules.
Good. Confirmation here in just a moment.
Or I guess 1,534 kilojoules. Yeah, I got the same.
Okay. All right, so kilojoules, well, let's figure out how many food calories it is. So let's convert to calories. So there are 1 calorie is 4.186 joules. Double check that just to make sure. Which would be 3,066.51 calories of the big C, food calories. So you take a ½ kilogram of ice, stick it in your mouth, keep it there till it steams at 120 degrees Celsius, which would mean that you have a fever probably. Actually, it probably means you're dead. I don't think we can withstand 120 degrees Celsius. Yeah, 120 degrees Celsius. Your brain probably would be boiling too. Like, yeah, you'd be in bad trouble.
I'm wondering how it would get that hot.
Yeah. When you're in heaven. I don't know if you've seen the thermodynamics treatment of the temperature of heaven versus the temperature of hell. And based upon quotations from the Bible, heaven is hotter than hell. It's worth looking up. So if you're just melting the ice, so I got a ½ kilogram of ice, I'm melting it. So that is roughly a tenth, very crudely, a tenth of the total. So you could, melting a ½ kilogram of ice, you'd burn off 36 calories, food calories. All right, questions?
So why is it called latent? Is it like leftover?
Latent is usually hidden. don't know. I mean, I could speculate that it's because you're not having it's not feeling hotter or colder. And so this is energy that's sort of hidden in there.
It's a hidden source of energy use.
Yeah,
Energy
that
just
works too.
disappears.
I blame the Europeans. I think they were doing a lot of the thermodynamic stuff early on, setting the standards. Or it could easily just be a mistranslation. All right, if you looked up a table of latent heats, sometimes they have positive, sometimes they have negative. And that's just a matter of here, I'm putting energy in, so I use a positive value. If I'm taking energy out, I'd use a negative. So if I were freezing a half kilogram, it'd be negative 166,500 joules. In other words, I'm pulling that amount of energy out of the water. But what about the others? So let's go to the triangle here. I have solid, liquid, and gas. All right, so the easy ones. If I go from solid to liquid, what is that called?
Melting.
Yeah. Go from liquid to solid.
Freezing.
So if you melt we're talking about positive 333,000 joules per kilogram. If we're freezing, negative. If I go from liquid to gas,
Evaporate.
Yeah.
Vapor or anything?
I would consider evaporating and vaporizing the same thing. Boiling means that you're doing that conversion based on temperature as opposed to, I mean, if I have the water here, it's eventually going to evaporate. I don't need to bring it up to any particular temperature. Evaporation or evaporating gas to liquid.
Was there another name for it though? I think there was
Vapor.
another one for solid to liquid as well. I don't know why I thought that.
Fusion?
I mean, it is sort of a
Something
fusing, but
condensing, but that's just, oh, that's what we're about. Okay, never mind.
where does condensing show up?
Was that gas to liquid?
Yeah, so condensing.
Okay.
Well, if they call it the latent heat of fusion, isn't that the name of the whole solid liquid conversion?
Yeah, just one's positive, one's negative. So
So that
this
whole
would
thing
be,
needs
so
to be-
freezing, the L sub F is negative, whatever, and melting L sub F is positive. The same number, same magnitude. Same here, positive, negative. What about solid to gas?
Sub something.
Sublimate?
Yeah.
Sublimating. There was a video I saw a couple years ago of someone making the claim that the snow we're seeing is some strange chemical because he took a blowtorch to it and you didn't see a pool of water. And in characteristic fashion that you would see on the internet, someone politely said it's called sublimating.
Is that
Gas to solid?
Deposition or something?
Yeah, there we go. I guess the same form depositing, depositioning. Depositioning sounds better than depositing. Now, if we're talking about, let's go for the typical stunning effects. So we melted here, so this latent heat of fusion was 3.33 times 10 to the 5th joules per kilogram. And then we evaporated, and so this was somewhere on there, 2256, 22.56 times 10 to the 5th joules per kilogram. But if I just went from solid straight to gas, what would that latent heat be? What is the latent heat of sublimation?
Is that 22 or 2.2?
It was 2.2 times 10 to the 6th.
Oh,
I made this 10 to the 5th.
Okay.
So,
Would it be the combination of both?
yeah, you just add them up, which is why I made them both 10 to the 5th. So this would be 25.89 times 10 to the 5th joules per kilogram. And then deposition negative, because you're pulling energy out. So we only need to give you two values there, and the rest you can just figure out. Questions to hear? All right. Let's take a break here, and I know you just got back, but let's take a break here, and then we'll get into some, well, in essence, what we're gonna do. First, we'll introduce one of the problems of classical mechanics, but not the solution. And then we'll push on from there, get into Carnot cycles, eventually solve the problem of if I've got a tent with a freezer in it, and there's there's an equilibrium temperature for outside, inside the tent, and inside the freezing compartment. If I stick another freezer in there that's identical to the first one, what would the new temperature in the tent be? That is where we're heading. So stretch your legs, and we will return with that. Probably time to plug this in and make sure it actually is charging. All right, so introducing sort of this new concept that the specific heat actually varies depending upon whether volume is kept constant or pressure is kept constant. And so these are molar specific heats. So the formula using these, if we keep volume constant, then the energy it takes is going to be the number of moles times the molar specific heat times change in temperature. Likewise, QP is equal to NCP delta T. And the book's using a capital C here for this, even though it's not just heat capacity, but the specific value, because it's not a standard. Now, before when I gave you the specific heat of steam, that was a lot closer to the CP than for the constant volume. Which makes some sense. I mean, if I'm boiling water, I'm definitely not keeping a constant volume there. All right, so let's bring in the first law of thermodynamics using the convention established last week. The fact that the change in the thermal energy, which we know is the kinetic energy of the particle level, is equal to Q plus W. Q is the energy put into a system, and work is work done on the system. By the environment. Because it's the net heat put into the system. So if you're putting energy into the system, you get a positive change in thermal energy. If you take energy out, this would be negative. And that would be a negative there, assuming no work was done. Let's take a look at the situations though. We have a CV and a CP there. So first let's take a look at the constant volume situation. So constant volume, otherwise known as isochloric. Iso being same and choric related to volume somehow. If the volume is staying the same, well, that actually affects the work. So let's take a gander at how the volume affects the work. Imagine that I have a gas here and a piston. If that gas does work on the piston, that means there's going to be a displacement there. So let's say that the piston will be moved up some value of delta x. So the piston is now up here, thanks to work done by the gas. I know that work is the integral of f dot dx. Since this is work being done by the gas itself, in terms of that W right there, there's a negative here. Since this is the work done on the system, this is the work by the system, it's going to be the negative of that work. When you start dealing with gases, dealing with the actual force that a single particle exerts on it doesn't make much sense. But it's the overall collective statistical thing, and so we start dealing with pressure. I know that pressure is force divided by area, and so therefore the force is pressure times the surface area. Assume a cylindrical piston, and so this is negative integral of PA dot dx. Surface area, where we'll go with the convention that the, oh, we haven't talked about area vector, did we? I know we do it in 252. Area vector, if you have a surface, for instance, think about this board right here, how would you define the area of a surface? How would you define the direction of the area of the board? We get the magnitude to length times width, but what about the direction?
It would probably make sense to do a normal vector.
And that's what they decided. So on a two-dimensional surface, I can have a normal vector going this way or the other way. The convention is that if it's a closed area or a closed volume, that the area, you pick the area vector to be a normal vector away from the center or towards the outside. So our area vector would be a vector in that direction. Now, if I think about this, the volume of this is going to be whatever the area is here times this distance, or that distance, depending upon if we're talking about initial or final. So my change in volume will just be the area times whatever the change in x is, I guess officially delta x. Or dV is equal to a dx. If we sort of hand wave away the dot product, I know that the area vector is pointing this way, the displacement's in the same direction, so just from the model that I'm using here, this is just PA dx. And ADX is just the volume, so this is the negative integral of PdV. So the work that the system does, we have a formula for it. Well, if the volume is constant, what's the work? no, you left something out. Or put too much in, depending on the way you wanna look at it. All right, so this is generically, if I had a pressure versus volume plot, and I had some curve like this is, ignoring the negative sign, this is the area under the curve. That's what the integral of PDV is. So if volume is constant, that's what the plot looks like. What would be the area?
0.
0. If volume is constant, then this term here is 0. Or pressure, therefore, is, I guess pressure changes, volume goes, yeah, it's 0. So in the isochoric system, my thermal energy is just equal to Q. Actually, QV, because we're keeping the volume constant, which is just the number of moles times the molar specific heat or constant volume times change in temperature. It's not earth-shattering, but it's getting us someplace. Now let's take a look at the constant pressure situation. Isobaric. I don't know if you're familiar with the terminology or not. Michael Jackson had an isobaric chamber that supposedly he slept in, according to the rumors. Well, we have a constant pressure. So if we think about that, looking at, again,